P, then we can find many quantities, many properties of the simple harmonic motion. So we can rewrite this equation like this, and then we say this is the second order differential equation. This differential equation is very easy to resolve. Now we resolve this equation by another way. So we use the reference cycles. We use the reference cycle to resolve this equation. So this is a cycle, and we call it is a reference cycle, and the cycle lies in the xy plane. So this is x-axis, and this is y-axis, and the origin or and the center of the cycle. There is a point. There is a ball, or there is a cube. This is a point, or this is a ball, and this ball is move around the cycle. So, and the ball is in a uniform cycle motion around the cycle. So the vector we can plot the vector. The vector is begin from center and point to the Q. So we say the vector of Q. So Q it is equal to A. So the length of Q is the magnitude. Sorry, is the amplitude. Well, we must know. This is the reference cycle, and the Q is move around the cycle. So we must let the OQ equal to A, or the radius of the cycle equal to the amplitude A. And the reference point Q, because the reference Q is to does the cycle motion. So the Q has angular speed, because this is a circular motion. In circular motion, there is angular speed. Angular speed omega is equal to 2 pi f, and is equal to the angular frequency. So this is is also equal to the angular frequency omega. Because for the Q the ball is to uniform circular motion. So for the circular motion, we also can introduce the angular speed and the frequency. So the angular speed. This is the speed actually in the circular motion, and in the same harmonic motion, the omega, we call the omega as the angular frequency. This is angular frequency. So the angular speed of the ball is also equal to the angular frequency. And the Q, all the ball does the motion, and the direction is counterclockwise. Now we can in Alexander, Q is the ball is at this position. So the OQ, the value of Q is in this direction. We can plot, or we can project the position of Q to the x-axis. So the projection of the OQ around x. So the x is equal to A cosine theta. The theta is the angle between OQ and the x-axis. And the P. So if there is a light x-axis. So when the Q is move around the cycles, then the shadow P will move along the x-axis. So yes, if the Q at this position, the P is at this point. And if the Q move to this, then the position is at this point, and move to this, then the Q is at this. Then the P position is at this. If the Q is at the bottom, at this point, then the position is at this point. So when the Q do some motion around the cycles, then the projection of P will move along the x-axis back and forth. So the cycle in which the point Q moves, so its projection matches the motion of the oscillating body is called the reference. You call it the reference cycle, because the projection of Q moves. The motion of the projection P is in the oscillation. So the ball moves in uniform through the motion, and so the shadow moves back and forth on the x-axis, and is in a simple harmonic motion. So now we try to find the motion of a point P. So we try to describe the motion of a point P. So when the Q is at this point, then the x is equal to a cosine theta, and the theta is the angle. The theta is the angle between the Q and the x-axis, because the Q is do cycle motion. So the theta is a function of time. So in uniform through motion, the theta is equal to omega t plus phi. The omega is the angular speed, and t is the time. So we plug this theta into this equation, then we can get the A is equal to A cos omega t plus phi. Then the t is the time. So we find the relationship between the x and the time. And this is the equation of a simple harmonic motion. So it is x equal to A cosine omega t plus phi. So this is the equation of the solution of the equation of the simple harmonic motion. And we must remember the form. We must remember the form of this solution. So this is cosine. This is cosine, and this is amplitude. And or we can say this is a coefficient. The coefficient is the amplitude, and this is omega. But the omega is in solar motion. The omega is the angular speed. But in the harmonic motion, the omega is the angular frequency, and the phi it is the initial angle. So there are three characteristic quantities of the simple harmonic motion. We will look at this A omega phi. So there is three characteristic quantities. First one is the amplitude. We are reading now is the magnitude of the maximum displacement, and it is in this figures. the A is the magnitude of vector or Q, and the second one, angular frequency. Angular frequency omega. So it is point Q rotators with constant angular speed omega quadruplied. So the angular frequency is equal to the angular speed. And the phase angle, the phase angle theta. The phase angle is this. The phase angle is this theta, and the theta is equal to omega t plus phi, and it is at t the vector of Q makes the angle with the positive x-axis. We must know that this is made with the positive x-axis, and especially at time t equal to 0, and then it is the phi is the initial phase angle. So this is not phi. It's not the phi is not always equal to 0. We must know. We just know the phi. It is the initial phase angle, and the initial phase angle will be not equal to 0. And we should know like this. The angle is made with the positive x-axis. Such as like this. At this position, the angle is the theta. If the Q is at this position, then the theta is the big angle. So we express the symbolic motion as the x component of the phasor alterity. The x is equal to a cosine theta, and the point Q is in universal motion. So the x component of the velocity is equal to the x velocity of the shadow p. So the velocity of the shadow, the x velocity of the shadow p is equal to v. We use Vx to refer to the x velocity of the shadow p, and it's equal to minus vq sin theta. We just look at this. The velocity of q is pointing to this direction, and the theta. This angle is the theta. This angle is the theta third projection, or the x component along the x-axis is equal to VQ minus multiply cosine sin theta, and this is minus. We should know this is the minus one, because so this is the minus, because when the theta is like this, when the theta is like this, the speed of the p is toward to left. The speed of p is toward to left. So we to right is positive and to left is negative, because we choose the right as the positive direction. Because the point Q is in uniform spherical motion, so its acceleration vector AQ is always directed toward the origin point, or in circular motion. In circular motion, this is R, the radius is R, and this is the body, and the speed is omega. Then the body, then the object has an acceleration, and the acceleration is constant, and is equal to omega square R. The omega is the angular speed, r is the radius. And in this situation, the direction is always along the radius and toward the origin. So this is the acceleration of the point Q, and we should find the projection of a Q along the x-axis. And so here x is equal to minus a Q cosine theta. So we look at this. The AQ is along this direction and point to the origin, so the component along the x-axis is equal to AQ cosine theta, and so AQ is equal to omega square A, so it's equal to minus omega square A cosine theta. Now look at this, the A cosine theta. So this is A cosine theta is equal to x. So we use x substitute A cosine theta, then is equal to minus omega square x. So the ax is equal to minus omega square x. So begin from the supermotion, we can find the displacement x, the velocity, and the acceleration along the velocity along the x-axis, and the acceleration along the x-axis. We just projection the quantity of the supermotion point Q along the x-axis. So at this point, firstly we can produce the vector along the x-axis, where we are given the x equal to A cosine theta, and then we can project the x. Project the velocity. Project the velocity of point Q along the x-axis. The velocity is in this direction. So the projection is equal to the magnitude is equal to VQ sin theta. But we must consider the direction, because we choose the right. We always choose the right as the positive direction. So, but this one is toward to the negative direction. So we must plus there must be a minus sign. And we can also find the acceleration along the x-axis, because the Q is in supermotion. Supermotion has a radius acceleration, and is always along the radius and point to the origin point, or the acceleration is in this direction, and the theta is there. This is under theta, so the projection is equal to minus AQ cosine theta, and the AQ is equal to omega square A. Then we can get A cosine theta, so it is equal to minus omega square x. So we can get the acceleration x is equal to minus omega square x. So from this equation we can get the acceleration of the point P is directly proportional to the displacement and always has the opposite sign. So the acceleration is directly proportional to the displacement x, and always has the opposite sign. So when x is positive, then x will be negative, and when x is negative, then x will be positive. So they always has the opposite sign in the x. And this one, and those are precisely the hallmarks of the same harmonic motion. So if we want to judge the oscillation is or not the same harmonic motion, first one we can find the form of the restoring force. Firstly, we can begin from the restoring force. Fx is equal to minus Ks. So if the residual force is in this form, then we can say the oscillation is the same harmonic motion. And if we find this one, you will find that the x acceleration is proportional to the displacement, and they have opposite side. Then we can say the oscillation is same harmonic motion. We can find the acceleration by two ways. The first one, the x is equal to minus omega square x, a squared. And the second one, the x is equal to the second derivation x with respect to time. dx square over dt square is equal to minus k over mx. So we can find the x by the two ways. However, the result from the two ways must be equal. So this one we must equal to this one. So this is the x, this is the x. So we can get this. The omega square is equal to k over m, and or we can rewrite the omega is equal to k over m root k over m. So the k is the first constant of this is the k. The k is the first constant. So if we find the residual force is proportional to the x and find the coefficient, then we can use this k in this term. And the m is the mass of the body. The omega. Now, the omega is the angular frequency. It's angular frequency. So the angular frequency is only determined from the force constant and the mass. So we must remember this equation. We can find the angular frequency from the force constant and the mass of the body. If the point Q makes one complete revolution in time t, then point P goes through a complete cycles of oscillation in